Okay, this is it. Last video in chapter 17 plus. We're talking about inverses of functions. We're going to talk about algebra, we're going to talk about geometry, but before we do any of that, we're going to talk about the notation so that we can recognize these when we see it. So we've talked a little about inverses in the past. We talked about inverse trigonometric functions and a reference inverses a little bit, I think 2 videos back. So let's just recap this. I've got 3 expressions up top here, and only one of them is the inverse, and that's this first one. So this is an inverse, okay? This second one here, that is a reciprocal. That means 1 over f of x, because we've got the exponent outside of brackets attached to the function. And then this third one over here, we've got the exponent attached to the x, so that's actually going to be f of 1 over x. So we need to really be careful with where the negative 1 is, because depending on where it is, it could really mean 3 different things. Generally speaking, when we have f n like this, of x, that generally does mean the same thing as f of x to the power of n, except when n is equal to negative 1. When n is equal to negative 1, this one means an inverse, this one means a reciprocal. I'm going to do my best most of the time throughout this course. If I want you to raise a function to a power, I'm going to use this notation most of the time. Not always. Be on the lookout for both. If you see one, you're not sure what it is, ask. But if it's negative 1, for sure, the one on the left, that is an inverse. The one on the right, that is a reciprocal. Now that we know how to identify an inverse, what the heck is it? Okay, so we have some idea of what the word inverse means. We should know what inverse operations are, right? Addition, subtraction, multiplication, division. Also squaring and square rooting, cubing and cube rooting, etc. These are called inverse operations because they do the opposite thing. If I add 3 and subtract 3, I get back to where I started from. So this function, this linear function, can be, in some sense, undone by its inverse. Now, I haven't explained how to find what an inverse is yet, so just trust me. This is the inverse of this. And they undo each other because if I were to make a composition of the two, for example, if I put the second one into the first, I'm going to have 2 times x minus 3 over 2 plus 3. Since I'm multiplying by 2 and dividing by 2, those 2 will cancel out. And now I have x minus 3 plus 3. Well, that's all just equal to x. It undoes it, and it just gets us back x alone. And if I were to do it in the opposite order, if I had put 2x plus 3 in for that x, we can do this one in our heads. We're going to have 2x plus 3 minus 3. The 3's will cancel, which gives us 2x over 2. The 2's cancel. We're just left with x. So that's what we mean when we say that inverses undo each other. Written in the language of compositions down below, if I take f of f inverse of x, that is the same as f inverse of f of x, and it's always equal to x. Last video we said most of the time the order of a composition makes a big difference. Inverse functions is another example where the order does not make a difference. If you take 2 functions, one of which is the inverse of the other, and you compose them in any order, your answer will always be x, or whatever your variable happens to be. So now, how do we find out what an inverse function is? Well, algebraically, what we're going to do is we're going to interchange. So we're going to switch x and y. They're going to trade places. And then we're going to make y the subject. In other words, we're going to solve for y in the new equation that we get. And this new one is the inverse function. And we can actually do this in either order. So this sentence says that we need to switch x and y first and then get y alone, but I'll show you in a second. You can actually start off by getting x alone in the original and then switching x and y. It doesn't matter at all. So here's an example where we have the one from the previous screen, y equals 2x plus 3. So first I switched x and y, so they just traded places in that line. And now I want to get y alone, so I'm going to subtract 3 from both sides, and then we're going to divide by 2. And that is our inverse function. However, we could also have started off by getting x alone, so I subtracted 3 and then divided by 2 all in one go, and then I'm going to just switch the position of x and y. There is one other thing I want to show you about the equations of inverses. So these two equations before you are inverses of each other. You can check my work if you want. Perhaps you could imagine putting this in for the x here. The first thing that's going to happen is that 32 will cancel with that 32, and then we'll just have 5/9 multiplied by 9/5 x, so those are going to cancel, and what we'll be left with is just x. And you could do the same thing in the other direction. So these are inverses of each other. But what I want to point out about their equations, a quick way to check your work besides putting one function into the other, is to look to see if the operations have all been switched and if their order has switched as well. So in the equation on the left, the first thing that happens is we are multiplying by 9/5, and the second thing that happens is we are adding 32. In the equation on the right, the first thing that happens is we're subtracting 32, and then we multiply by 5/9, or perhaps we should say that we divide by 9/5. So again, on the left, we multiplied by 9/5 first. On the right, we divided by 9/5 second. On the left, we added 32 second. On the right, we subtracted 32 first. So all of the operations were changed to their inverse operations, and the order was reversed as well. And the reason I chose these two functions is because they're a pretty famous pair. These are actually the equations to change between Fahrenheit and Celsius degrees for temperature. If I have a temperature in Celsius and then I convert it to Fahrenheit using the first formula, and then I take that Fahrenheit value and I convert it back to Celsius, of course I've got to end up back where I started again. So clearly these two equations are inverses. So finding an inverse function isn't really that bad. What does it mean graphically? Right? Like, how is this going to change the graph? It's kind of like a new type of transformation, but it's certainly a more wild one than any of the ones we've seen previously. It is the reflection of the original function, not over the x-axis, not over the y-axis, but over the line y equals x. So that's a line through the origin with a slope of 1. Tuck that away in your mind. We're going to use that in just a minute. Before we go on, let's talk about the domain and the range of an inverse function. So what can we say about that? Well, since the domain is all the possible x values and the range is all the possible y values, but with an inverse function, we are switching x and y. That means that when we compare it to the original function, we're also going to switch the domain and the range. The range of the original function is the domain of the inverse, and the domain of the original function is the range of the inverse. We're just switching x's and y's. Now I've been talking about inverses, and I've probably even been saying inverse functions, but you know what? The inverse of a function is not always a function itself. I'll show you a simple example here. Let's say we have the function y equals x squared. If I want to take the inverse, that means x equals y squared, and then I need to solve for y, which is going to give us y equals plus or minus the square root of x. And I know that that's not a function because If I put in one particular x value, say I put in 4, then y could be equal to plus or minus 2. And a function is going to have one y value for each x value. So even though this is technically the inverse, we could call this the inverse relation, it's not actually a function. How could I tell from looking at a graph whether the original function has an inverse that is also a function? Again, it all comes back to switching x's and y's. So how could we tell looking at a graph if it's a function at all? Well, we had something called the vertical line test, right? If we drew a vertical line and it crossed our function more than once at a particular point, like at a particular x value, then we said that it was not a function. To determine whether it has an inverse that is a function, we're going to use the horizontal line test. So if we have a graph and it passes the vertical line test, it's a function. If it then passes the horizontal line test, then it also has an inverse function. Incidentally, you don't need to know this for this course, but if this is true, if we have a function whose inverse is also a function, then that function is called one-to-one. Just throwing it out there. You may see it in a future math course. I fear that that ending part might have been a lot. I really think it's easier than I may have made it sound. I feel like I just talked a lot, and it's not that bad. Let's just play with graphs for a second. Don't worry about what these equations are. I just want to show you some pictures. Is this a function? Yes, passes the vertical line test. Is its inverse also a function? No, because it fails the horizontal line test. How about this thing? Is it a function? No, it fails the vertical line test. Is its inverse a function? No, it fails the vertical line test. Next, function? Yes. Inverse function? No. Next, function? Yes. Inverse function? Also yes. Cool. Function? Yes. Inverse function? No. Function? Yes. Inverse function? Yes. Function? Yes. Inverse function? No. Function? Yes. Inverse function? Definitely not. Its inverse function is going to be a vertical line. I mean, and this clearly fails the horizontal line test. Function, yes. Inverse function, no. This is a vertical asymptote here happening at 5. It's not like actually filled in. They're getting really, really close to 5, but never quite touching it. Last one, function, yes. Inverse function, yes. Again, it looks like it's getting horizontal there, but it's not perfectly horizontal. It actually has an asymptote, so it is actually getting just closer and closer and closer to 0 as we move out here to the left, but it never actually touches it, and so it's never actually flat, so it does have an inverse. So identifying whether a function is an inverse and whether its function is an inverse should be really easy. You should be able to look at a picture and tell pretty much immediately, again, whether it's an inverse and whether its function is an inverse. Let's do a problem. So we've got this function going on here, 1/2 x minus 1. Oh, it's a line. Thank goodness. That makes it simple. Find the inverse function. Okay, let us start there. So if we just switch the x and y, then we've got x equals 1/2 y minus 1. And if we solve that for y, we get 2x plus 2. Now, generally what we want to do is not just leave it as y equals 2x plus 2. We want to really label that as f inverse of x equals 2x plus 2, because that notation really tells me this is the inverse of that. And we can tell that from the name, f inverse compared to f. So I really want us to try to do that instead of just writing y equals, write it as f inverse. Next, let's check that f of f inverse is equal to f inverse of f, which is all equal to x. Okay, we know this is always true of a function and its inverse, but this is a nice way to check to make sure that we've done the work correctly. So we can just do two compositions of functions, and we find that they both equal x. Letter C. So we want to sketch both of these on the same axes. Okay. So we should be able to, okay, these are both lines. So we should be able to sketch them both easily enough. But what do we notice here? When we look at the picture of both those lines together, we notice that one is the reflection of the other over the line y equals x. We said earlier that was always going to be the case for inverse functions. So again, let's play around just a little bit here. So here's our line, our axis of symmetry, if you will, y equals x. And here's the two functions from the previous question, and we see, that, again, like this one is the reflection over y equals x of this one. Something else to notice, by the way, since we're switching x and y, that means that any point lying on one graph, so for example, the y-intercept here is at 0, 2. If I switch x and y, I get 2, 0, and that's going to be a point on the other graph. And that will be true for any point on either one. If we switch x and y, we're going to get a point on the other one. I just have a couple of other simple inverses ready to go here just so we can see them. So this is the graph of y equals x cubed, and its inverse, this is pretty simple to calculate, is going to be the cubed root of x. And we see again that one is the reflection of the other over the line y equals x. If you're having any difficulty seeing this, please tilt your head 45 degrees to the right. Here's a function y equals 3 over x minus 2. You can check the algebra if you want, but its inverse is 3 over x plus 2. And again, those are reflections over this line. And last, here's something we're about to study. It's called an exponential function, compared to something that you'll cover in a future course called a logarithmic function. But those two are inverses of each other. And again, those are reflections over the line y equals x. So if you have the graph of a function, you should be able to draw a sketch of its inverse really quickly because you're just going to draw the thing reflected over the line y equals x. If you know any exact points on the original graph, like here I know it goes through 0, 1, that means that on the inverse function it's definitely going to go through 1, 0. Again, the domain of one is the range of the other. When I look here at this graph, seems like its domain is probably all real numbers. It seems like its range is only going to be values that are bigger than 0. When I look at its inverse, its domain appears to be x values that are bigger than 0, but its range appears to be all real numbers. It goes down towards negative infinity, and as we go out here to the right, it is increasing forever. It's increasing very slowly, but it is continuing to go up and up and up and up and up, so it is going to go up towards positive infinity eventually. So here are three functions. These are all functions. We're going to determine if their inverse is a function, and then if it is, we're going to draw a quick sketch, and then we're going to state the domain and range of both. So our first one here. Well, if I check the horizontal line test, it pretty clearly fails it. So this first one does not have an inverse, so I'm not going to bother with any of the stuff they're asking for, because they only want it if it has an inverse function. And, you know, really in like common speak, if it's not an inverse function, we'll usually just say it doesn't have an inverse. Technically, it does have an inverse relation, but you'll probably catch me saying it doesn't have an inverse, so you can say that too. We'll understand each other. Anyway, second example, this is just a line segment. Every line is going to have an inverse function as long as that line is not a horizontal line, right? Because a horizontal line, when we switch x and y's, we're going to get a vertical line. So that's clearly not a function itself. But everything else is going to be fine. And this just being a segment of a line, it clearly is going to have an inverse. And then this thing here, whatever it is, that looks like it's going to have an inverse. Clearly passes the horizontal line test. So we're going to sketch both of those and then state their domain and range. So for a sketch of this one, I would consider the original here. Here's our line y equals x. And we're just going to like reflect it over. Now, if you're worried about like, oh, I want it to look really neat, well, just switch the x's and y's. The first endpoint of the given one was 0, -1. That means that our reflection is going to start at -1, 0. And it ends at 4, 2, so our reflection is going to end at 2, 4. That's all you got to do. The domain of the original was from 0 to 4. Those were the possible x values along there. That means that the range of the inverse will be from 0 to 4. The range of the original was -1 to 2. That means that the domain of the inverse will be from -1 to 2. It's all about switching x's and y's. For this thing here, before I even show it to you, let's predict. What point do we know will be on the inverse? Well, we only know one point on the original. That's -2, 0. That means that the inverse will have 0, -2. It does. So we'd plot that point first. We would kind of draw in our little reflection axis here, and then once you've got that in, you can kind of just draw in the general shape of it. Don't be a perfectionist. It doesn't have to look absolutely perfect. Just, give me the general idea. The domain of the original appears to be from -2 all the way to infinity, or just x greater than or equal to -2, and that's the range of the inverse, y greater than or equal to -2. The range of the original appears to be y greater than or equal to 0 because it's increasing. Therefore, the domain of the inverse is x greater than or equal to 0.
This is something that works for me, for my brain. It might also work for you, I don't know. It's a way to help you visualize what an inverse is going to look like. So here I've got my x and y axes, and I'm labeling them positive and negative, because this is going to be important when I switch my x and y's. I need to make sure that the x positive and the y positive switch positions, and the x negative and the y negative switch positions. So here's what I'm going to do. I'm going to flip my paper over and then rotate it. We can see, because I've done this in Sharpie, that x plus and y plus have switched, and x minus and y minus have switched. And that means that whatever function I decide to draw into this thing, I don't know what I'm going to do. Let's do something weird like this, because I want it to have an inverse function. The inverse of that looks like that.
Now, it's possible when we switch x and y, and then we solve for y, that we get the same function we started off with. Or it's possible, thinking graphically, that when we take a graph of a function and we reflect it over the line y equals x, that we get the exact same picture that we started with. This is something called a self-inverse function. So it's where f of x is the same as f inverse of x. The example given here is 1 over x, and that's definitely a self-inverse function, because if we switch x and y, and then we solve for y again, so here I'm multiplying by y and then dividing by x, I get the exact same thing that we started with. The line y equals x is also technically a self-inverse function, because if I switch x and y, I get the exact same thing. There are other self-inverse functions as well. There's nothing particularly important or interesting about them other than the fact that they are their own inverse, and that's the end of that. So we're going to end things there. So to recap, this is our notation. The -1 is on the f. That is not an exponent. Please do not say f to the -1. Please say f inverse. I will correct you every time, hopefully more and more obnoxiously the more and more you say it. A function and its inverse are always going to cancel out, so they're always going to give us x as the output whenever we compose a function and its inverse. We're going to find an inverse by swapping x and y, just having them switch positions, and then solving for y again. And the domain and the range are going to therefore switch as well. And if, graphically speaking, a function and its inverse are reflected over the line y equals x.